My name is Duanmu Haojie, a second-year PhD student from Shanghai Jiao Tong University. I'm really delighted to introduce our paper, SKVQ, Sliding Window Key and Value Cache Quantization for Large Language Models. By the way, this is actually my first paper, so I'm very excited to be here to give the presentation. Okay, so the background of this work is that KV cache becomes a critical memory bottleneck in LLM inference system. To avoid some duplicated computation during the large language model inference, we usually cache the key and value activation generated by the attention module, and this part of memory consumption is called KV cache. And on the one hand, nowadays, the model context is getting longer and longer. As can be seen from the first figure, when the sequence length is beyond 8,000, the KV cache generated by Llama 2 7 billion takes more memory than the model weight. On the other hand, in the real-world deployment for large language model on data centers, the batch size is usually large. And as the batch size increases, the memory footprint of the KV cache will gradually increase and exceed the model weight. And the KV cache size can be simply calculated by the formula. So how to reduce the memory footprint of a KV cache becomes a key issue in LLM deployment. Reviewing the formula of KV cache size calculation, there have been a series of work trying to reduce the memory footprint from various aspects. KV cache eviction only returns KV caches of a fixed length and discards the rest according to some policies. Layer-wise sharing will share KV cache of similar layers. And multi-query attention, global query attention share multiple query heads to the same KV heads, reducing the number of KV heads as to reduce the KV cache size. Another perspective is to reduce the element size of KV cache. In large language model inference, typically we use 2 bytes data types such as IP16 or BF16. However, do we really need 2 bytes for each value? Many studies have shown that the weight of LLM can be quantized to 8 or even 4 bits, almost lossless. We can also quantize KV cache. During the inference, we use asymmetric min-max per token linear quantization to compress the original 16 bits KV cache. And we only store this low bitwidth cache. For example, if the original 16 bits KV cache is quantized into 4 bits, then the storage of KV cache is 4 times smaller. And when performing attention computation, we dequantize them into 16 bits with some quantization error. And our experiments show that using the existing per token quantization method, directly compressing the KV cache to 4 bits only brings minor accuracy degradation. However, once it comes to 3 bits, the model shows significant accuracy degradation. So, can we do better than this? The answer is, of course, yes. One of our motivations comes from the locality nature of attention module. The locality nature is that the attention module pays more attention to the most recently generated tokens in each time step. As shown in the figure, the most recently generated tokens receive higher attention score, and we propose a hypothesis that it's more important to preserve the token cache accuracy within the local window. And in addition to the local window, there are other critical tokens, for example, the first few tokens. On top of these patterns, we design a sliding window quantization strategy Specifically, we maintain a fixed-size sliding window covering the latest KV catch. When a token catch pair slides out of the window, we choose whether to quantize it to low bitwise. And as you can see, the result of our ablation study shows that by simply adding a sliding window on top of the existing per token quantization, we can significantly improve the performance of the quantized model. This is very simple but very effective. Next, for the quantization technique, we find that the numeric distribution of the KV catch is the main culprit for the drastic accuracy degradation. This figure shows the distribution of different channels in two token catches. From the figure, we can get some important observations. First of all, there is a huge variance between different channels, which leads to huge quantization error. The reason behind this is that the per token linear quantization is essentially an affine map. It maps the real value of the channels to the post-quantized space. And these huge magnitudes will occupy almost all the range of the quantized numeric representation. As shown in the figure, almost all other values except the outliers are compressed into the same representation. And one of the solutions to this outlier problem is smoothing, which is proposed in smooth quant. It uses a per channel smoothing factor to smooth different channels. However, we also observe that the magnitude of values vary between different tokens. This means that the per channel smoothing factor may shift the numeric distribution of different channels, so that it will lead to performance degradation, especially in extremely low bitwise quantization. Third, we know that the concept of outlier in previous study is relative. Channel 1 is an outlier channel with respect to channel 8. However, the channel 8 is also an outlier channel with respect to channel 9. So we propose a better solution to this outlier problem, and it's called channel clustering. Okay, so the red box in the figure indicates a quantization group. In the existing per token group quantization, we form a quantization group from several adjacent channels, and the values within one quantization group will share the same quantization parameters. And in our method, instead of group adjacent channels, we cluster channels with more similar numeric distributions. Then we reorder to gather the channels in one cluster together to form a quantization group. We find the clustering highly reduces the number of outliers within a group. Okay, and we also use group clipping to further elevate the outlier problem within one group. For each quantization group, instead of using min-max to compute the quantization parameters, we multiply them by a value between 0 and 1. This helps to further improve the quantization accuracy. And after this transformation, we can significantly reduce the quantization error of group quantization. And it comes to the experiments. Since KV catch quantization is mainly meaningful in long contest scenarios, we use the long contest benchmark, long bench, for testing. This benchmark contains various types of tasks, which is consistent with real-world scenarios. Experiments result on Mistral 7 billion show that our method consistently outperforms the existing method at various average bits, and at around 2 bits. It's close to the full precision baseline. We also extend our experiments to large-size model, Llama 3 70 billion. With 2 bits KV catch, our method achieved more than 98% of the baseline on most tasks. And we also conduct experiments on needle in haystack with context length set to 32,000. And the results show that our method is far superior to existing per token quantization. And a comparison with Kiwi under different settings also shows a better score, and we find that under the setting of key catch 2 bits, value catch ternary, the 1.5 bits indicates the ternarization, yeah, and our method is almost lossless. In conclusion, we first propose a sliding window quantization strategy which can significantly improve the performance of the KV catch quantization in long context scenarios. Then we use clipped dynamic quantization with channel reorder to reduce group quantization error. And our method achieves beyond 7 times memory footprint reduction. It allows 1 million tokens in single A180 GB GPU. Okay, that's all. Thank you.